Module 5 Complex Variable Residue Integration. The first section of Module 5 is Lorenz Series. Lorenz Series generalize Taylor series. That is, if we want to develop a function f of z in powers of z minus z naught, where f of z is not analytic at a point z naught, then we can use a new kind of series called Lorenz series. Before going to the definition, first of all we analyze the region of the integration or where f of z is defined. Let C1 and C2 be two concentric circles with the center at Z0. Let C be an any closed curve between the circles C1 and C2. Also, f of z is analytic the annular region or the blue shaded region or the between two circles C1 and C2. That is, the Lorenz series defined as follows. Let f of z be analytic in a domain containing two concentric circles and with the center Z0 and the annulus between them. Then f of z can be represented by the Lorenz series as f of z equal to summation n equal to 0 to infinity an z minus z0 the whole power n plus summation n is equal to 0 to infinity bn divided by z minus z0 the whole power n. We can write it as equal to, first we substitute n is equal to 0 for the first term, that is a0, then 1, that is a1 into z minus z0 plus a2 into z minus z0 the whole square plus dot dot plus, then I substitute for 0, n is equal to 0 for the second term, we got it as b0 plus b1 by z minus z0 plus b2 by z minus z0 the whole square plus dot dot. That is, which is consisting of non-negative and negative powers. Then the coefficient of Lorenz series can be defined are given by the integrals. An is equal to 1 by 2 pi I integral over c f of z dash divided by z dash minus z naught the whole raised to n plus 1 dz. Bn is equal to integral over c f of z dash divided by z dash minus z naught the whole power minus of n plus 1 dz dash, taken counterclockwise around any closed path C that lies in the annulus region. That is, C is an any closed path where f of z is analytic. For the first example, find the Lorenz series expansion of the function f of z equal to z raised to minus 5 sin z. That can be written as sin z divided by z raised to 5. For the practical purpose or the problem solving sessions, we are playing or we solve or we write the Lorenz series expansion using the Maclaurin series or Taylor series. As we know, sin z is equal to z minus z cube by 3 factorial plus z raised to 5 by 5 factorial minus like that. Then the question is sin z by z raised to 5. Then we can written as of 1 by z raised to 5 and substituting the values of sin z as a series representation. It is a Maclaurin series of sin z. Then operate the bracket 1 by z raised to 5 into z, that is 1 by z raised to 4. Then 1 by 3 factorial z square, 1 by 5 factorial minus z square by 7 factorial plus etc. That is, which include positive terms and negative power terms. This is the Taylor series expansion of z raised to minus 5 sin z. Check the second example. Find the Lorenz series expansion of z square e raised to 1 by z with the center at 0. That is a familiar result for Maclaurin series. E raised to 1 by z, that is equal to 1 plus 1 by z plus 1 by 2 factorial into 1 by z plus 1 by 3 factorial into 1 by z cube plus 1 by 4 factorial into 1 by z raised to 4 plus dot dot. That is, we know the expansion of e raised to z. Replace z by 1 by z, we got this series. That is Maclaurin series of e raised to 1 by z. The question is f of z equal to z square into e raised to 1 by z. First I write z square, then in a square bracket I substitute e raised to 1 by z's expansion. After that, operating with z square, then z square into 1 by z, we got z, then 1 by 2 factorial, then 1 by 3 factorial into z, then plus 1 by 4 factorial into z square plus etc. like that. Which is also a Lorentz series expansion which contain positive power terms and negative power terms. Next, example 3. Find the Lorentz series expansion of 1 by z raised to 3 minus z raised to 4 with the center 0. That is f of z is a given function 1 by z raised to 3 minus z raised to 4. From the denominator, z raised to 3 is common. I take it as common. That is 1 minus z. That is 1 by z raised to 3 into 1 minus z the whole raised to minus 1. Then 1 by z raised to 3. Then I write the series expansion of this one, 1 minus z the whole raised to minus 1. That means 1 plus z square plus z raised to 3 plus z raised to 4 plus dot dot dot. Operating this one, we got it as 1 by z square plus 1 by z square plus 1 by z cube plus 1 by, there is a printing mistake, 1 by z cube plus 1 by z square plus 1 by z plus 1 plus z square. Next question. Find the Lorentz series expansion of e raised to z by z minus 1 the whole square with the center z naught equal to 1. Please check, the center z naught is equal to 1. That means the expansion containing the powers of z minus 1. That is, put z minus 1 equal to t, therefore z equal to t plus 1. That means the function f of z equal to e raised to z by z minus 1 the whole square. That is e power, instead of z I substitute e raised to t plus 1 divided by z minus 1 the whole square. That is t square. Z minus 1 equal to t, therefore t is t square. The objective of this substitution is convert this question into we can apply the Taylor series or Maclaurin series of the basic series. That is e raised to t into e raised to 1 divided by t square, law of exponents. Then e is a constant, I write same by t square. Write the value of e raised to t. 1 plus t square by 2 factorial plus t cube by 3 factorial plus t raised to 4 by 4 plus dot dot dot. Operating with 1 by t square, that is 1 by t square, 1 by t, 1 by 2 factorial, t by 3 factorial plus t square by 2 factorial. Then this contains the negative powers and positive powers of t. Then resubstitute t is equal to z minus 1, that is e of 1 by z minus 1 the whole square plus 1 by z minus 1 plus 1 by 2 factorial into z minus 1 by 3 factorial plus z minus 1 the whole square by 4 factorial plus dot dot dot. Actually it is mod of z minus 1 greater than 0.